In November of 2018, a spacecraft that had already been flying for 41 years crossed into a region of space no instrument had ever directly sampled before, and almost immediately it measured something that shouldn't have been possible according to nearly every assumption scientists had built up over decades of studying our solar system's edge. The magnetic field out there in the supposedly separate foreign territory of true interstellar space was pointing in almost exactly the same direction as the magnetic field back home. Not a coincidence anyone could easily explain away. Not a fluke of measurement, a second, independent confirmation of something Voyager 1 had glimpsed years earlier. And scientists still, to this day, do not have a confident explanation for why it's happening. This is a real, published, peer-reviewed mystery, sitting at the edge of our entire solar system, and it's one of several genuinely strange discoveries Voyager 2 has handed scientists, since it became only the second human-made object in history to leave the protective bubble surrounding our sun. Every finding in this video comes directly from peer-reviewed research published in Nature Astronomy and public statements from the scientists who actually conducted it. Not speculation, not exaggeration, just the genuinely open, unresolved reality of what these two aging spacecraft are still teaching us. Let's start with what Voyager 2 actually confirmed, because to understand why it's so strange, you first need to understand what scientists expected to find instead. Our entire solar system sits inside something called the Heliosphere, an enormous bubble of charged particles and magnetic field lines generated by the sun and blown outward in every direction by the constant stream of the solar wind, a continuous flow of charged particles racing outward from the sun's surface at speeds often exceeding 1,000,000 miles an hour. Think of the heliosphere like a ship sailing through the vast ocean of interstellar space, its own bubble of influence pushing outward against the surrounding medium, carving out a protected region where the sun's magnetic field dominates everything inside it, from Mercury all the way out past Neptune and beyond. Beyond that bubble lies true interstellar space, the actual territory between star systems, filled with its own separate plasma, its own separate radiation environment, and scientists generally assumed its own separate independent magnetic field, shaped by entirely different forces than anything happening within our own solar system. Forces tied to the broader structure and history of our galaxy rather than anything our own sun has ever influenced. That assumption is exactly what Voyager 2's data challenged. When the spacecraft's magnetometer, the instrument specifically designed to measure the direction and strength of magnetic fields, took its readings just beyond the heliopause, the actual boundary separating our solar system from interstellar space, the field it detected pointed in a direction nearly parallel to the magnetic field found just inside that same boundary, back within the heliosphere itself. Scientists had actually seen a hint of this same strange alignment years earlier, when Voyager 1 made its own crossing back in 2012. But at the time, with only one spacecraft's worth of data, researchers genuinely couldn't tell whether that alignment reflected some real physical property of the boundary itself, or whether it was simply an odd coincidence tied to the specific point in space and time where Voyager 1 happened to cross a single data point that could easily have been dismissed as a statistical fluke rather than a genuine feature of the boundary itself. Voyager 2's own magnetometer readings, gathered 6 years later at a different location along the heliopause, entirely independent of whatever conditions Voyager 1 happened to encounter during its own crossing, settled that uncertainty. The two datasets agreed. The magnetic fields on both sides of the boundary really do appear to align, and that alignment is not simply a one-off fluke unique to a single spacecraft's specific crossing point. Why does that matter so much? Because it directly contradicts the intuitive picture most people, including many scientists working in this field, had assumed for decades. If our solar system's magnetic field and the wider galaxy's interstellar magnetic field come from entirely separate sources, shaped by entirely different physical processes, there's no obvious reason they should line up with each other this precisely, especially not at the exact boundary where one supposedly gives way to the other. It would be a little like expecting the current in two completely separate unconnected rivers to happen to flow in exactly the same direction the moment they reach the same stretch of coastline, purely by chance. Researchers studying this data have been genuinely candid about how unresolved this puzzle remains. As one summary of the findings put it plainly, why the fields appear so aligned remains one of the great puzzles of heliophysics, the scientific field specifically dedicated to studying the sun's influence throughout the solar system and beyond. This wasn't the only genuinely unexpected result Voyager 2 delivered once it crossed into interstellar space. In November of 2019, 5 separate papers, each covering data from one of Voyager 2's 5 still operating scientific instruments at the time, a magnetic field sensor, 2 instruments detecting energetic particles across different energy ranges, and 2 separate instruments for studying plasma, were published together in the peer-reviewed journal Nature Astronomy, painting a detailed combined picture of exactly what the spacecraft found at that boundary. One of the clearest results confirmed something scientists had actually predicted correctly, that the plasma in interstellar space is significantly denser than the plasma found inside the heliosphere, and noticeably colder as well. That part matched expectations, and it served as an important independent confirmation that Voyager 2 really had crossed into a fundamentally different physical environment, exactly the kind of clean expected result that gives scientists confidence the rest of their instruments are working correctly too. But alongside that confirmation came another surprise. Rather than fading out gradually, the way many scientists had originally pictured the transition between the heliosphere and interstellar space unfolding, something closer. To a slow, blurred gradient stretching across a wide, indistinct zone, the actual boundary Voyager 2 detected was remarkably distinct and sharp, almost like a genuine wall rather than any kind of gradual transition. Researchers involved in analyzing the data suggested the overall shape of the heliosphere itself likely resembles something like a blunt bullet, rounded and compact on the leading edge facing the direction of our solar system's motion through the galaxy. An image considerably more specific and structured than the simple, smooth sphere many earlier, simplified models had assumed, and one that required real, careful analysis, combining data from both spacecraft's very different crossing points to actually piece together. There's also a genuinely important safety dimension buried inside all of this research, one that connects directly to the practical question of what protects life here on Earth. Beyond the heliosphere, both Voyager spacecraft detected a sharp, unmistakable increase in galactic cosmic rays, extremely high-energy particles accelerated by distant, long-dead exploding stars scattered throughout the galaxy. Particles energetic enough to pass through solid matter and potentially damage living cells if they reach a human body unshielded. Voyager 1's own data helped establish that the heliosphere functions as a genuine shield, blocking more than 70% of that incoming radiation from ever reaching the inner solar system, including Earth itself, a protective effect most people go their entire lives without ever thinking about, simply because it's always been there, quietly doing its job since long before humanity existed to notice it. That protective effect isn't just an abstract scientific curiosity. It's directly relevant to any future plans for long-duration human spaceflight beyond our solar system, since understanding exactly how that shielding works and how reliably it holds up over time matters enormously for predicting what kind of radiation exposure astronauts might eventually face on any journey far enough to actually test those limits, whether that's an extended mission to Mars or, in some far more distant future, an attempt at genuine interstellar travel. And yet, even with two independent spacecraft now providing direct measurements from beyond that shield, researchers are candid that the exact mechanics of how the heliosphere's protection actually works, and how consistently it holds up under different conditions, remains only partially understood. Then, in October of 2020, came another finding that added an entirely new layer to the puzzle. Astronomers reported a significant, genuinely unexpected increase in plasma density detected independently by both Voyager 1 and Voyager 2. Despite the two spacecraft having crossed into interstellar space at completely different locations and at different points in time, 6 years apart. That shared, unexpected density increase suggested something scientists hadn't previously confirmed, that this density gradient isn't just a local, isolated quirk near wherever each individual spacecraft happened across the boundary. It appears to be a genuine, large-scale feature stretching across a meaningful portion of the very local interstellar medium surrounding our solar system, a detail that reshapes how researchers think about the actual structure of the space immediately outside our cosmic neighborhood. Merav Ofer, a space physicist at Boston University who has spent years studying this data, summarized the overall situation with a level of honesty that I think deserves real credit, admitting plainly that scientists now know how little they actually know about the heliosphere, describing it as far more complex and far more dynamic than anyone had previously assumed. That's a genuinely striking admission from someone whose entire career is built around studying this exact region of space, and it captures something important about where this field of research actually stands right now. This isn't a settled, fully mapped out picture with just a few decorative details left to fill in. It's an active area of real, ongoing scientific uncertainty, being slowly, carefully worked out using data from precisely two spacecraft, both of them approaching 50 years old, both of them running on rapidly dwindling power. That power situation adds real urgency to everything. Researchers are still trying to learn from this data. Both Voyager spacecraft, weighing only about 720 kilograms each, roughly 1,600 pounds, are now operating in what NASA has openly described as survival mode, a deliberate, carefully managed state where non-essential systems, including onboard heaters, have already been sacrificed simply to keep the core spacecraft and its remaining instruments alive as long as possible. Both Voyagers carry a specific instrument called the LECP, or Low Energy Charged Particle Detector. that has become a genuine engineering marvel in its own right, and one that has directly contributed to nearly every finding described in this video. It includes a small stepper motor designed and tested to survive exactly 500,000 steps over a planned 4-year operational lifespan, rotating the instrument in 45-degree increments every 192 seconds, so it can continuously scan in every direction as it gathers data. By the time researchers were documenting its performance in 2024, that same motor had already completed close to 8 million steps across 42 consecutive years of continuous operation, roughly 16 times longer than its original design specification ever called for, a fact that Stimatios Crimigis, one of the instrument's principal investigators, has described with genuine undisguised amazement. It's worth pausing on that number because it means a single mechanical component, spinning quietly and continuously since the late 1970s, has been directly responsible for gathering much of the very data that revealed the magnetic field, alignment mystery, the sharp heliopause boundary, and the density gradient findings described throughout this entire video. As of early 2026, both Voyager spacecraft remain more than 13 billion miles from Earth, and remain, remarkably, still operational, still communicating, still adding new data to exactly the kind of open questions this video has walked through. But every instrument still running is running on borrowed time, and every answer researchers still hope to extract from this unique, irreplaceable dataset has to be pulled out now, while there's still a signal to receive at all. There is currently no other mission anywhere close to reaching interstellar space to take over this work once these 2 aging spacecraft finally go silent. And if a dedicated new mission were funded and launched today, current projections suggest it would take at least another 2.5 decades to reach the same boundary Voyager 2 crossed back in 2018. So here's what I actually want you to take away from all of this. When Voyager 2 crossed into interstellar space, it didn't just confirm a boundary existed. It handed scientists a working physical mystery, a magnetic field that inexplicably lines up with our own solar system's field, despite having no obvious reason to, a boundary sharper and more structurally defined than anyone predicted, and a density gradient stretching across a genuinely large portion of the space immediately surrounding our entire solar system. None of these findings have full, confident explanations yet. They're open questions, actively being studied right now by a small community of scientists working with an irreplaceable, rapidly aging dataset that simply cannot be replicated by any other mission currently in existence. That's not a comfortable, tidy story with a clean resolution. It's real, ongoing science, unfolding in real time from a machine that has already outlived every original expectation anyone ever had for it. And there's something worth appreciating in that discomfort rather than rushing past it. Every open question described in this video represents a genuine gap in human knowledge, not a failure of the mission, but proof of exactly how much this small, aging spacecraft has managed to teach us simply by successfully surviving long enough to reach a place nothing else we've ever built has gone. Bill Kurth, a space physicist who has worked on the Voyager mission since 1974, has described this outcome as transforming what started as an exciting planetary mission into something closer to an expedition of humanity itself. A description that feels genuinely earned given everything these 2 spacecraft have quietly handed back to us since leaving Earth nearly 50 years ago. If you want to know the moment scientists finally figure out why that magnetic field alignment exists, subscribe and turn on notifications, because researchers are still actively working on exactly this question using data these 2 aging spacecraft continue sending home. And drop a comment telling me what you think is actually causing that alignment, because right now, genuinely, nobody knows for certain, and I have a feeling whatever the real answer turns out to be, it's going to change how we think about the space immediately surrounding our own solar system.